Welcome to this course on FPGA based signal processing systems. So, in this lecture we will be looking at the modeling of digital circuits. What are the different types of modeling in the Verilog? First, the parameter declarations, the module which has the declaration and the statements that we had looked into the previous lecture, all the declaration types, input declaration, output declaration, net declaration and variable declaration. Now coming to the parameter declaration. So it's a type of constant which needs to be declared. So suppose port ID, here it's given over here, port ID is a variable which is defined as equal to 5, or it should be assigned a value 5. So the 5 is fixed. If when you say parameter port ID equal to 5, the 5 is assigned to port ID, and which is defining the constant. Similarly, port ID, instead of port ID we have the cache line width. So for example, this is 256 the width of the cache line is 256. So the parameter is declaration is used to assign the value 256 to specify the width of the cache line. Also the width, the WITDTH, that is the width is 16 bits signed, then it can be a 16-bit value of signed, can be fixed sign, and the range of parameters also can be range also can be specified with the parameter. So the examples of this which we have taken, the module and gate module, where the input and output, now the declarations now try to simplify the lines of the code, which is module and gate, that is input x comma y and output is z. So we have put that input x and input y, our input x comma y as a separate declaration. So in the port name itself we can define this with a comma. If we say input x comma y comma, then x and y are inputs and the output z is output. Now the declaration can be simplified in the parenthesis itself. So the port name itself, this is just we try to move on to the simplification of the core declaration part as well. So if we take another example, that is wherein VR328 DCA, that DECA is a module name. So module name should start with the letter, and it can have the numbers and underscore and dollar and so on. So the input wire, so the wire declaration also can be merged with this in the port name G1, G2, G3. So all of them are inputs that, and said that net type is wire, and the input wire again it can be a multi-bit also. So we can specify this A is 3-bit input wire and wire type, and y 0 to 7, that is 8 bits output register. So we can combine these declarations in the port name itself. So instead of having the declaration part in a separate lines, you can have it in this fashion as well. So now coming to all the declaration parts, and there are in the Verilog module we have the statements. So the statements are concurrent statements. So according to these statements, how we use what is used in the Verilog codes that are in the Verilog module is we can classify them as 3 types of modeling. One is the structural modeling, and the data flow modeling, also the behavioral modeling. So the structural modeling, so suppose for example we talk with this, we try to learn this with an example, so to understand it better. So the structural model gives as such in the digital circuit what we have. So if we take the model of the structural model, the module Verilog code for a particular structure, the digital circuit, here we take this is an AND gate for example. So this AND gate is simple AND gate which we want to describe this inputs and the output. So in a structural model, so the module, every module of the Verilog will have the module and end module and the module name. So here we had given AND underscore gate underscore structural. So this is the module name, and then we try to define the port names. So the port names we give here is this A, and B and Y. So A, B are inputs and output is Y. So the input need not be repeated here. That can be, as we have seen in the previous slides, input A comma B, that would also suffice. So output is Y. So these are the port names, 2 inputs and 1 output. The declaration can also be input A, input B, input A comma B as a separate line also. Our output Y, that way also we can define the declaration. So this is the module, end module, module name and declaration part is done. So now coming to the statements. So the Verilog module contains the statement parts. So the statement here in the structural model as such, which is available in this. So here, and if you see, and is a keyword, and is a built-in gate. So G1 Y comma A comma B and semicolon. So this G1, we are naming this gate as G1. Okay, so then as G1 and its output is in the bracket. So that means we are instantiating the built-in gate here with the name, and G1 is the name which we had given here. It can be anything as per your choice, and within the bracket Y comma A comma B. Y is the output. So always the output should come first and then the inputs, number of inputs A comma B, and it can be a 3 input gate as AND gate as well. So if you have 3 input AND gate A, B, C, so this is as such the input and the output, how in the digital circuit the logic gate looks like, or any of the multiplexer or the demultiplexer or decoder, coder, encoders and so on can be modeled in the fashion. So we are going, this is a very simple model which is using the primitive gates or the components of the Verilog. This is using AND. So for our gate, we can just simply change this with the OR and G1 Y A comma B. So if you want to write for a structural model, so this is for logic gates. You can use the built-in gates, XOR gate, and all of the built-in gates available in the Verilog. So now coming to the data flow modeling. So the data flow modeling is giving the functional description of the circuit. So for example, how the data flows from this input to output. So in the case of data flow model, so what we have, this AND gate is again for AND gate, we have this module and end module, and the module name is AND gate data flow. So and the input output declarations, we have for input A and input B, output is Y, as we taken in the example. Now the declaration part is over, and coming to the statement is that assign. So this assign is a keyword. Okay, so assign is a keyword where Y equal to the AND gate example, A and B and Y. So the Y is assigned a function, that is A and Boolean function A and B. So AND is a bitwise AND, you can see the AND ampersand symbol, A and B. So this is how this A and B change. Whenever there is a change in this A and B, Y gets changed. So it's also called as continuous statement. Assign statement is called as a continuous statement. Change in A and B will be reflected in Y immediately. So this is the bitwise AND of data flow model. So we will be differentiating these models. You may not be appreciating with the AND gate that models in the difference. So you see, instead of having this AND built-in gate, so we use the function of this, the Boolean function of this gate as A and B, Y equal to A and B. That is the assign statement. So we are going to look at this, all the statements separately. So these are concurrent statement. Anyway, for a simple example, I am giving it here. This is assign is again a keyword that should be in a different color, like input, in output, and module and end module. And the behavioral model, so there is a third modeling type, that which is the behavioral description, like any other software languages. So the AND gate, again the AND gate example, we have giving you the behavioral model. Module and end module have this module name as AND gate behavioral, and the declaration should be same. And I would you can notice this reg declaration over here. Okay, so this can be output Y, we can declare it, or output and reg Y, separate declarations can be. So the declaration can be input A, B, these are single bit, and then output it is y, and that is also reg. This is also this will make the code lengthy. So output reg y. So that we combine these declarations in the port name itself. So still there is a possibility to combine these two, input a comma b. So the code, the behavioral description of this, it's an always statement. That's always at the rate of a or b. We can say this in the always statement at the rate, this is called the sensitivity list. So sensitivity list will contain these signals which is required for the circuit. So here a or b are the inputs, which both are defined, are mentioned in the sensitivity list, a or b. Here y equal to a and b, that is procedural assignment. Like this is a bitwise and again within the always block. So y equal to a and b. So this is also similar to that assign statement, but that is a continuous assignment in the case of previous data flow model, how the data is flowing, or data flow from input to output, whereas in the behavioral description how this circuit behaves. Okay, so a and b, whenever there is a change, this always block will get executed always at the rate of a or b. So if there is a change in a or the change in b of the inputs of the AND gate, so then in this a and b will be calculated and assigned to y. So this y is inside the always block, that is a behavioral description. That's why we define this as a reg declaration here. So this will change, this will store the value, this y will store the value. So that is why it is declared as register. Okay, so we don't have the multiple statements here, we have only one statement. Structural, that is all in the structural or in the assign statements, all are these concurrent statements. In this case, it is within the always block, the statements are sequential. But multiple always block, if you have these always blocks will be concurrent. So we will be looking at these in detail, that how the behavioral description and the data flow, also the structural description will vary. So three different models of the digital circuits are these. So we will be digging out further in detail about these three models. For example, again the structural model of OR gate. For example, I told you this gate structural, the input a and b gate. This is actually optional. G1, you can call this OR gate as G1, and here is a and b, and this is y, built-in OR gate. So the data flow similarly for OR gate have this send statement, and y line the OR symbol of this Verilog, a line b, that is the bitwise OR. Assign is a keyword here. This is a continuous statement. So behavioral model similarly always at a or b, so give a the line b. Okay, so it is not necessary to have this always block in this case, but the procedural assignment is for this example. So we will differentiate these three in the further examples. So coming to the example of this half adder, let's take this structural model of the half adder. So in the Verilog module and half adder, which would add one bit numbers, two 1-bit numbers. So here half adder is a module. Again the input a, b and sum and carry are the outputs. So we have the input, we will give the diagram of this a and b, and there is an XOR gate here, and then take this a and b and give to AND. This is sum, you will get a carry over here. So simple half adder, how this structure is going to be. So in the description or the statements, this concurrent statement XOR, this is XOR gate, XOR, and this is AND. So the XOR, this is named as G1 and this is G2. Okay, so G1 and G2. So XOR we call the built-in XOR gate. G1, what is the output of it? It is sum, and input is a and b. So sum comma a comma b. So with this is sum XOR. It will do the operation of XOR. Okay, so it is just a command to give this XOR option. G2 carry, which is a and b, that is going to be G2 and AND gate. AND gate. So in the data flow or in the behavioral, we can use this XOR or A and B operations. So G1, G2 are the optional, the names given to the gates. So how it is connected, that A and B are taking as input, and there is no line or the wire or the circuit is unconnected here. So we have mentioned this AB, output also sum and output is carry. So these two can be simplified, and this also can be simplified, input A comma B and then output sum comma carry. That is also possible to simplify this code further. So this is and one more thing here, in the structural modeling we have this XOR gate as well as the AND gate. First we had written the XOR gate and then AND gate. So the order doesn't matter here, you can first call the AND gate and then XOR gate as well. So this is also a way of instantiating the XOR, the gates. The built-in gates are XOR and AND. The built-in modules for XOR and AND are instantiated here. So the XOR, and we give the module name, that is G1, which is optional, and the output comma input, two inputs. So this is these are concurrent statement. This is called the concurrent statements. So the order in which it appears doesn't matter here actually. So it can be the first AND gate can be written, and then XOR can be written next also. So this is not a sequential statement, these are concurrent statements. So like any other program, this is not sequential. The structural model, we have these concurrent statements. So whereas in the always block, what I said, that within the always block or within the initial block, the behavioral description, these are sequential, the execution is sequential. Here XOR and A and B. So this half adder, and then we have this modules and the declarations, and this is the data flow model. So in the data flow model, this assign keyword sum A XOR B. So the semicolon, this is XOR sum. Okay, so we are not calling here or instantiating the XOR gate as in the case of structural model. Here assign, the carry is A and B. So the AND for carry. So these are bitwise operations anyway. So these assign statement is continuous statement, assign sum and carry. So this is also a concurrent assignment or concurrent statements. It's not a sequential statements here. And coming to the behavioral model. So the behavioral model, the module have this N module, half adder, input A, B, output which you can see the difference, output reg, sum and carry. So always the declaration part is done in this case, always at the rate A or B, the same for this OR gate. This R is nothing to do with the OR gate. So if you mention A or B, that means signal A or signal B. Whenever there is a change in A or B, this gets executed. So we have multiple statements. So I have this begin end blocks. Begin, yes, sum is A XOR B, that is an XOR operation, and sum is equal to A XOR B, and carry is equal to A and B. This is end. So this is these two, sum and carry, are getting the values A or B, A XOR B, and our carry is getting A and B values whenever there is a change in A or B. So this is sequentially executed. So the sum is sum, after that carry. So here the order matters in the begin end block, they always at the rate. So even if you have only one statement, it doesn't need to include begin end in this case. So the reg declaration is essential because it is storing this value within the description or the always block. So we have to define this as a reg, which is driven by these signals. So reg declaration, the output is a reg signal. So far we have not used the wires in the declaration. So let us the difference between this AND gate, OR gate, or the half adder, that it doesn't have the connection between the elements. So let us see this, for example, the multiplexer. So if we say take a 2 into 1 multiplexer, 2 into 1 here. So here we have the inputs x1 and x2, two inputs, and S is the select line. So if S is 0, S equal to 0, then this becomes 1, and whatever x1 and 1, this AND gate will give G, and if s is equal to 1, then this AND gate will be depends on x2, this will give H, and that is G and H are ORed to give F. Okay. So F will be what is either it is giving x1 or it is giving x2. So the values assigned to it. So let's see the module now. So we can see the connection between the AND gate and OR gate. Here also this OR gate and AND gate. So there are two connections, and also between NOT gate and the AND gate. So here is there are between connections we have the between the elements we have these connections. So let's see how to handle this in the structural model. So as such, what is drawn over here, so we need to write it in the code. So module and N module, we give the module name as multiplexer. The inputs are declaring that x1, x2 and S are the three inputs, and output is F, only one output they are taking. So now basically this multiplexer will be given as 1 and 2, and there is a select line. This is x1 and x2, and you have F here. So select is a single bit, that is one bit, 0 1 0 or 1. So here I am declaring something here as wire. So you can see wire K, G and H. Okay, so these are connecting the output of one element to the input of the other. So this needs to be declared as wires. This is a physical connection between the two ports. Similarly, G, you can name it anything, G and H will also be the output of this AND gate is connected to input of this OR gate. Similarly, G is connected to this. Okay, so we can name these gates even G1, G2 and this is G3. Okay, in that way. So there is first instantiation here is a NOT gate. Okay, so it can be any gate G1, G2 or G3 because these statements are going to be concurrent. So then these are concurrent statements. So the declaration part is over till this point. Okay, now NOT K and S. So input NOT we are instantiating. I've just not given any of the, suppose this I assume this name as get4 G4, and here this option of G4 would come, G4 K comma S. K is the output and S is the input. And the AND gate here, this G1, give this G1 the optional name, and the output is G, small g, and the input is K and X1. So K and X1 are inputs. K is defined as here is a wire. Okay, so this is wire. So basically this is capital K, sorry. And then AND gate, and similarly AND, this is H, and the input is S and X2. So this S and X2 are again the S and X2 are the inputs to the gate. So here we can write this, it is G2. Okay, so the option. So initially to start with, it is better to have this all in the design the gate name specified, or you can name them 1 2 3 gates, and then writing practice this Verilog codes G2 and G1 and G2, and now the NOT gate is instantiated, G1 is instantiated, and then G2 is instantiated. Now the OR gate, the next one, the G3, this is G3, this we can say G3, the output is F and input is G and H. So this K, G and H, all of them needs to be wire, declared as wire. Otherwise you see that here this G and H are what, there is no declaration if suppose this is not done. Okay, so the code doesn't understand what is that K, G and H are. So in between the elements, hardware elements, the wires are connected. So in the structural modeling, so these are the physical connection, the connectivity between this two hardware elements. So K needs to be defined, and similarly G and H are the between G1 and G3 and G2 and G3. So if you look at the structural code in this module, so module and N module, we have the module name and the declarations. Apart from inputs and outputs, we need to find the declaration of this connections between the hardware elements, that is G1 and G2 or G3. So K, G, H needs to be declared here. This is anyway 2 to 1 mux, and F is the output. So if select is 0, x1 will be passed, and then if select is 1, x2 will be passed. So this way this multiplexer would work on this module and n module F, G, H. So the instantiations, again the NOT, and OR, this can be in any order. The concurrent statement will take care of that. If whichever the signal is first changing, then the corresponding will be executed, and then the next, and so on. So this is the structural modeling. Can we take this of the data flow model, how this data flow occurs? So in the same case, like the module, n module multiplexer, and input in 2 inputs in and the select line, this is another select line is another input, third input, output is F. So assign this F as, so now you see the function of this, what is the Boolean function going on here. We are not bothered about this is the primitive gates as we did in the structural one. So now we look at this AND function is getting this k and x1. Okay, k and x1 are the NOT of this delay. So even this k need not be defined here in this particular example. So here F is equal to, if you look at the within the bracket tilde s, that means tilde s represents the NOT gate operation, NOT operation. So this is giving the k value. So yes, tilde s and x1, this is and that is going to be G. So this will be giving the G of output, and the next one is S and x2. S and x2 are ANDed, this gives the H. So G and H are ORed with this in the OR gate. So we write in a single line instead of having so many instantiations in the structural modeling. Structural modeling is good when the design expands, like if you have so many gates and the other elements in your design. So then it is cumbersome to write the Verilog code for the structural modeling. So the design expansion will move, you have to move to the either data flow modeling or the behavioral description. So assign F, this is continuous assignment. So F is tilde S and x1 and S and x2. So this is a single line code which describe the multiplexer here. So the next one is the behavioral model. So in the behavioral model, the similar what is the description we have? This is using the always block. So module, multiplexer, x1, x2, S and F. Now we see this x1, x2, S and F. What are these port names? x1, x2, S are inputs. So for a change it has been done. It is also easy to combine it in the port names. Output is F here. So the x1, S, x2 and the F, and there is a reg F which I had shown you in the AND and OR gate examples as well. So always at the rate x1 or x2 or S. So all the inputs are in the sensitivity list. So x1 or x2 and S. So these are either any change in x1 or x2 or S signals, then execute if check whether the condition if statement, if S is double equal to 0, this is a logical equality. If check whether S is equal to 0, if it is 0, then this becomes 1. Okay, S is 0, this becomes 1. So x1 whatever is x1 will be passed on to G, and so F will be equal to x1. Okay, so if it is 0, this will be giving 0 and x1 will be passed on to F. F is equal to x1. So F is storing a value here within the always block, that is a procedural code. So declare this F as reg, and it is seen only in the inside the module. It is not seen outside the module. The reg declaration is not seen outside the module. It is inside. It is only inside declaration. So here F x1. Else if S is not 0, S is equal to 1. Okay, S is equal to 1, then this will be enabled, or this will give the output, and F will be taking the values of x2. So F equal to x2. It's very simple. So if else statement. So also we can have this if else statement where we have the multiple because we have only one condition, we can even add this begin end in this always block. So this execution is sequential. So always if first it checks s is equal to 0, then f equal to x1, else f equal to x2, so an end module. So this is the behavioral description of the multiplexer, 2 to 1 multiplexer. So now we know this, what is the wire declaration, how does it work between. So wire declaration doesn't come in the case of the behavioral description. Okay, so you can have this very simplified code or the functionality, what is the behavior of the circuit. So we are describing through this code that the behavior of the circuit. So it's a behavioral description or the procedural code, like the other any other languages. So this input in the declaration part, which includes reg declaration, that is the only add-on to the other types. So coming to the full adder example. So full adder, you can consider that the circuit which is inside, I think we will be knowing, and or we will be doing this. So there are two A, B and the carry in input as well. So you're adding the two inputs, and the other one is that the carry which is coming in also to be considered in the full adder. So the output is sum or Cout, sum and Cout. So the module, n module, the full adder description. So you have the input A, B, input C in also, output sum, output Cout. I am explicitly defining this input and output declaration. You can combine this as well. So full adder, FA is the full adder name, module name. So the data flow model, it gives this assign. So simply assign sum, that is going to be just a description of the Boolean function. So we know that it is going to be then XOR function. So the A XOR B XOR C in. So we say that A, B and C in are the inputs. So this is going to be a XOR, and this output is again made as XOR and get the sum. Okay, so this is the two gates which are not a structural model. So you can check for the structural model also. The two gates are written in one line. So A and B are XOR, and then the result of this is XOR with C in, then get this Boolean function sum. Sum is that. This assign is a continuous statement, and then how this data flow from here. So and then the Cout assign, so which takes this A, B as one AND function, we know that and B and C in as another AND function. Also C in and A is going to be the another AND function. So these three will be ORed to get Cout. So the OR function, so this is ORing, this AB is this AND, B C in and C in A, and the OR bitwise AND OR is given here. So the assign Cout is calculated with this Boolean function. So assign statement, two assign statements will be working on that. So it's a data flow modeling of the full adder. So half adder can be instantiated inside the full adder. That is also another way of doing the Verilog code. So initially I just give this as a full half adder separately and full adder diagram. Even this can be simplified, the full adder description can be simplified further. So it's just to understand this data flow structural modeling and then behavioral description. So one bit, this is the full adder. Again, what about the other modules? Like can see the structural model. I would just give this thing what we have given. So module, full adder name, that is module name, the inputs X, Y and C in, that is what we have taken, and the sum and the Cout are the outputs. So here inputs are declared as X, Y and C in, and the output is S and Cout declared. And this is for the structural model, how this one bit full adder is done. So first XOR gate, so it is named as XOR S1, that is S1 is the output. You can name it, simplified names also can be used. XOR S1, this is the gate name, this is optional name, and XOR S2, this is also a second XOR gate, which is, so the outputs and inputs can be seen over here. So the input is X and Y, so it is given here. The input of this is S1 and Cn, so the S1 and Cn, whereas the output is S1 here and the output here is S. So these are the two outputs. Two XOR gates are instantiated, and then three AND gates. So AND C1, this is AND C2, and this is AND C3. So these three of them are instantiated one by one. So the inputs are here X and Y. So the input is X and Y for the first AND gate, and the second AND gate X and C in, and the third AND gate has Y and C in are the inputs, comma separated one, and the outputs are C1, C2 and C3. So C1, C2 and C3, so three AND gates are instantiated. So the first two OR gates over here, and the next three AND gates, and the left out one is this OR gate. So the OR gate gets the input from C1 and C2 and C3. So the C1, C2, C3, and the output is C out. So this is given as RC out here. So this is RC out. So OR gate is instantiated here. So all the gates 1, 2, 3, 4, 5, 6, all of this 6 gates here are instantiated one by one. The order in which it is going to be, the way in which the order doesn't matter, because these are concurrent statements. So it executes. We'll talk about this concurrency also in the coming lectures. So wires, you can see, if you notice, especially the wires are, because when you instantiate it, you are just talking about the input and output, the declaration, when the modules are getting input and output signals. But the output here S1, it's an intermediate one which is not declared here in the port names. Also C1, C2, C3 are not known to the module. So these are known X, Y, C in, S, C out. Okay, but what about this S1, C1, C2, C3? So that S1 is between which two hardware elements? So XR S1 and SR S2, so that needs to be defined as wire. And similarly, and S1 and C1 and R C out, that is a C1, the wire, physical wire within this is C1, also should be declared as wire. And the next one is C2 over here, and C3, all of them needs to be declared as wires. That is essential in the case of structural modeling. So this is about the 1-bit adder, structural modeling, and we had also seen the data flow modeling. So in this lecture we have looked into the different modeling of the digital circuits. One is the structural as data flow and the behavioral description. So how this blocks, this like always statement and the assign statement, and what is the case of concurrent statements and sequential execution within the always statement. These things we'll be looking at, in the details are need to be told. So that we will see in the next lecture. So right now to give the fundamentals of the structural as well as the data flow and the behavioral, using 3 different examples I had given here. So we'll see them, and we explore this further in the coming lectures. Thank you.